Si os sembla, comencem. Empiezo dando los buenos días a todo el mundo en 3 idiomas, si puedo. Bon día a tothom y gracias por estar aquí. Vamos a ver si me atrevo a decirlo en vasco. Egunon gustoi eta eskerrik asko egoteagatik. And we thank you for being here today. First of all, we hope all of you and yours are well, and our best wishes to those who have gone through or are going through difficult times. For us, this colloquium is very special, as it is the first activity, and we hope that it will be not the last one, which is carried out jointly by the Basque Center for Applied Mathematics, BCAM, and the Barcelona Graduate School of Mathematics, BGSMath. For this occasion, we have organized a double session with Gábor Lugosi, which is an ICREA researcher at Pompeu Fabra University, and José Antonio Lozano, which is the scientific director of the BCAM. Both are, in addition to top-level researchers, excellent communicators. We are deeply grateful to them, to both of them, for agreeing to give the talks, and we hope you enjoy them. And just to begin, some kind of optimization of the listening of the talks. As you are already very used to that, we ask you that you mute the microphones and to turn off the videos during the talks. And at the end of the talk, those who want to ask a question, please raise your hand so that you can ask your question by unmuting the microphone. So just to begin, saying that our first speaker is Gábor Lugosi, who works among other lines of research in theory of machine learning, combinatorial statistics, random graphs, and random structures. And today he will talk about mean estimation, statistical and algorithmic problems. Please, Gábor, you can begin when you are ready.
Okay. Thanks very much. Thanks for the invitation. It's great to be here, whatever here means. It is a really great honor to give this colloquium talk. So let me try to share my screen. What's happening? Yeah, can you see this?
Yes.
Okay, great. Okay, so I have about an hour, right?
Yes.
Okay. Okay, so today I'm gonna talk about probably the most basic problem in statistics, which is estimating the expectation, the mean of a random variable, or more generally of a random vector. So in the first half of the talk, I will only talk about the one-dimensional case, just to present some of the ideas, and in the second half, I will extend this to the multivariate, multi-dimensional case, which presents some exciting challenges, somehow unexpected after 100 years of statistical research. Myself, when I started to work on this problem, I was surprised how many things are open and how many nice problems there are. So what I'm gonna tell you today is mostly based on joint work with Shahar Mendelson. At the end, I will give you a list of references of our papers that appear here. Okay. Please feel free to interrupt if there's anything unclear or. Okay, so here's the setup. It's really the most basic setup where we have independent, identically distributed observations of a real random variable, and we assume that the expectation is finite. Okay, so because otherwise estimating the mean doesn't make sense. So we would like to estimate the expected value of this random variable. Okay. So what is an estimator? Estimator is just any measurable function of the data. Okay, and an estimator generically will be denoted by mu and hat. Okay, so we would, of course, this is a random quantity, and we would like this random quantity to be close to the true expectation. Okay, so in what sense does this make sense? I will say a few more words about this. Okay? Now, of course, you can say that, of course, if you want to estimate the expectation, then let's just take the empirical mean. Everybody does that, right? Let's just compute averages, and that should be a good estimator. Well, in a sense, this is true because we know that without any further assumptions, the strong law of large numbers tells us that that asymptotically the empirical mean converges to the expectation, right? And this convergence is with probability 1. So with 100%, we can be 100% sure that eventually this estimator will get close to the expectation. Okay, and if we are not willing to assume anything else about the distribution, only the existence of the expectation, then in fact this is the most you can say. So this convergence can be arbitrarily slow, and in particular the slow convergence can be caused by heavy tails, right? If some values, some really large values can happen with high probability, then this average can be pretty bad, and one can construct distributions such that this empirical average will converge arbitrarily slowly. And in fact, you cannot even do better than this. Okay, if we have no further assumptions on the distribution. Okay, good. But what if we know a little bit more? So, for example, we may assume, and this is a common assumption and really not a very strong one, that the variance exists. So, what the variance is just the expected squared difference from the expectation. Then all of a sudden we can say many more things. Okay, for example, the mean squared error. This is statistics 101, right? On first year undergrad statistics. The mean squared error equals the variance divided by n. Okay? And this is true for all distributions whose variance is finite. And in fact, this is optimal. So even if we know that the distribution is really nice, for example, if we know that the distribution is Gaussian, then this is the best estimator. You cannot beat this. Okay. And I think it is because of this very nice property of the empirical mean, which is it's optimal with respect to the mean squared error, why people weren't really looking for other estimators, because for a long time the way of measuring, the standard way of measuring the quality of an estimator was this mean squared error. Okay? However, the situation changes dramatically if we are not interested in the mean squared error, which is somehow an integrated error, but we are interested in bounds that hold with high probability. Okay, so let me explain what I mean by this. Wrong direction. Okay, so the question that I'm gonna ask in this talk is that, let's say we have some given probability of error that we are allowed to make, then what is the smallest value of epsilon, which may depend on this delta, it may depend on the sample size, it may depend on the variance, such that we can guarantee that with probability at least 1 minus delta, the estimator is within distance epsilon of the true mean. Okay, so I call this a confidence bound, right? So let's say if delta is 0.01, then what we ask is that we want an estimator that is with probability 99% is within epsilon. So how small can this epsilon be? Okay, that's the question. Now, of course, we have Chebyshev's inequality, and the Chebyshev's inequality tells us that we can take, if mu n hat is the empirical mean, then we may take sigma divided by root n times root delta. Okay, so this shows that the same kind of phenomenon that we already saw from the mean squared error, that the typical error decreases as 1 over square root of n as the sample size grows, and it's proportional with the standard deviation, which is the square root of the variance. Okay. All right. Now, we also have, without any more conditions, we also have this wonderful theorem that's called the central limit theorem, that roughly speaking, what it tells us, this is not exactly the central limit theorem, but it's a corollary of it. I'm ignoring only very minor factor. What it says is that asymptotically, the probability that the error is larger than sigma times square root of log 1 over delta divided by n, I'm just ignoring the constants, is less than delta. So what this means is that at least asymptotically, we can take this epsilon from the first slide to be sigma over square root of n. So that's the same that what's suggested by Chebyshev's inequality. However, here we have a square root of log 1 over delta instead of the 1 over square root of delta. Okay, so that's an exponential improvement over what we get from Chebyshev's inequality. Okay, so the central limit theorem suggests that the dependence on delta should be exponentially better than what Chebyshev's inequality suggests. Okay, however, here this inequality is only an asymptotic guarantee. While Chebyshev's inequality is true for every n. Okay, for every distribution, for every n, we have this guarantee. Okay. So where I come from, which is machine learning, and people are really not interested in asymptotics. So somehow asymptotics is old school, and even though we're talking about big data, lots of data points, the dimensionality of the problems that appear in machine learning is so big that we cannot. These asymptotic results are often useless. So one really would like to have non-asymptotic guarantees, like the one that Chebyshev's inequality says. But wouldn't it be nice if we could replace this 1 over delta by square root of log 1 over delta? Okay, and this is really important because in many applications, one is interested in not just estimating one expected value, but simultaneously we may have millions and millions of problems, and we would like all of them to be accurate. But then if we want to, then this delta has to be something like 1 over many millions in order for this to make sense. Okay, so the delta that we are interested in usually is really, really small. So Chebyshev's inequality is basically useless. So if delta is 1 over 100 million, then we are screwed unless n is some astronomical value. Okay, but here this logarithmic dependence is really gives us hope. Now, so the question is, can this be made non-asymptotic? Well, the answer is yes and no. For some distributions, this can be done very easily. For example, if the distribution is what we call sub-Gaussian. So sub-Gaussian just means that the formal definition is here is that the moment generating function of x is bounded by the moment generating function of a Gaussian random variable with variance sigma squared. So if x has this this property, which kind of intuitively means that the tails of the distribution go down really, really fast, even faster than Gaussian, then one can make the central limit theorem, this inequality that we get from the central limit theorem, non-asymptotic. Okay? So in particular, we have that with probability 1 minus delta, the error of the empirical mean is bounded by sigma over square root of n. And now the dependence on delta is exactly what the central limit theorem suggests. Okay? But this is a very, very strong condition. Okay? So the question is, can we, are there sub-Gaussian estimators? So we call this a sub-Gaussian bound. Okay? Sub-Gaussian bound when we have, when the distribution, sorry, when the error of the estimator behaves as if it was a Gaussian random variable, or even better. Okay? Now, if the distribution is not sub-Gaussian, then Chebyshev's inequality is unfortunately the best we can say. So it's not difficult to construct examples in which you see that the empirical mean will be this bad. Okay, with probability at least delta, the error will be bigger than what Chebyshev's inequality says. Okay? And this is, as I said, really bad news because this dependence on delta prohibits from using the empirical mean as an estimator when we want to estimate many expectations at the same time. Okay. Okay. So now the question is all hope lost, or are there better estimators? Can we maybe dream up estimators other than the empirical mean that have better properties? And the maybe surprising answer is yes. There are several very simple estimators that for free give us sub-Gaussian performance. So one of these estimators is called the median of means estimator, which is a very simple trick that many smart people invented. So I think the first appearance is in the book of Nemirovsky and Yudin, and then independently other people whose main research was not about estimating the mean, but they kind of needed this kind of tricks. They came up with this estimator independently of each other. So what do? We simply take divide our data into blocks. So there are k blocks, each of them of size m. Okay, so I just assume here that n, the sample size, equals k times m. Okay, so we take k blocks. Within each block, we compute the empirical mean, and then we take the median, the midpoint of these empirical means. Okay, so this is called the median of means because we take small independent chunks of the data, we calculate the empirical mean, and now we take the midpoint of this. Okay, and here's this beautiful inequality that says that if we choose the block size appropriately, meaning if we take roughly log 1 over delta blocks, then with probability at least 1 minus delta, we have that the median of means estimator has this beautiful sub-Gaussian, non-asymptotic sub-Gaussian property. Okay, so the probability with probability at least 1 minus delta, the median of means estimator differs from the true mean by no more than sigma over square root of n times something that's proportional to square root of log 1 over delta. Don't pay attention to the constants. I haven't optimized them. We lose a little bit, but not much. Okay. So this is wonderful and kind of surprising that, and this is true. Under the only assumption that the variance exists, that sigma is finite. Okay. So by departing from the empirical mean and doing something just a little bit smarter, a little bit more clever, we can be for free. We get a sub-Gaussian estimator. So I will show you the proof because it's just 2 lines. It's here. Okay. So what we know is that we can use Chebyshev's inequality in each of these blocks. Okay. So what we know that for each block is within distance. You see, m is the sample size in a block. So is within distance sigma over square root of m with probability, let's say 75%. Okay. But that means that we expect that 75% of the blocks are within this distance. So now, in order for the median to be far from the mean, we need that at least half of the data points are also far from the mean. But the probability of that is now exponentially small because the probability of that is bounded by the probability that a binomial with k independent flips, remember these blocks are independent, whose success probability is at most 1/4, right? That's what we get from Chebyshev here, is bigger than half of k. Okay? But this is exponentially small in k by standard bounds for the binomial distribution, and that's how we get this one. Okay? All right, I have zero feedback from the audience, but I hope that this is understandable. Okay, so the median of means estimator has this really nice properties. It's sub-Gaussian. It scales automatically with sigma with the variance. You see the parameter only depends on delta, the desired confidence. Okay. Now, of course, this parameter does depend on the confidence level, and Now you may ask, of course, the empirical mean doesn't need to know anything. It just takes the data and computes it. Now, here, this estimator will be different. You want it to be accurate with 99% probability, or if you want it to be accurate with 99.99% accuracy. So the estimator itself, the number of blocks that we use here, depends on the desired confidence level. Okay, so it would be nice to have an estimator that actually is independent of the required confidence level, but we can prove that this is impossible. So there's no estimator that does not depend on delta that has a sub-Gaussian performance for each delta, okay, under this general conditions. It's also nice that even if we don't assume the existence of the variance, but we assume something less. So let's say we assume that moments of the order 1 plus alpha exists for some alpha that may be less than 1. You see, if alpha is 1, then this is just the variance, but alpha can be arbitrarily small. And if we assume the existence of moments just a little bit more bigger than 1, then one can get a similar bound where you see now alpha here replaces the 1 that we got before. Okay? And in fact, one can show that this is the best one can do in a strong sense, in the sense that if you give me a number m and the value alpha and the confidence level delta, which is which is at least exponentially small, and any mean estimator, you can cook up your favorite complicated mean estimator, then I can give you a distribution whose 1 plus alpha's moment equals m, and such that the error will be larger than this quantity. Okay, so what this says is that the median of means estimator is optimal in this minimax sense for a large class of distributions. Okay. The proof is here, 2 lines. It's not difficult to show this optimality. I'm not going to go into the details. Okay. So what's one important consequence of this is that you see from this lower bound, we see that even if we want a rate of convergence, if we want the error to be of the order of 1 over square root of n, then we do need the existence of the variance. So if the variance doesn't exist, then there's no hope even to get an error that decreases with the sample size as 1 over square root of n. But as soon as the second moment exists, then we not only have 1 over square root of n rate, but we also have this beautiful sub-Gaussian inequality, right, which is here. Okay, so it's sigma over square root of n times the dependence on the confidence, which is of the order of square root of log 1 over delta. Okay, so this is a kind of magic. There's a big kind of phase transition when the variance exists, and this explains why we are after sub-Gaussian performance, because as soon as the second moment exists, we do have the sub-Gaussian bounds, and that is actually the best, even if we assume much more. Even if we know that the distribution is Gaussian, you cannot do better. Okay? All right, so here's another idea, still in 1 dimension. This is a different estimator. This is what all practitioners would do. This is called the trimmed mean estimator. Okay, so what's the trimmed mean? Of course, the problem with heavy tilt data when you can have very large values is that it will bias somehow the empirical mean. It drags the empirical mean. If you have a really large value on one of the ends of the distribution, then it somehow pulls the empirical mean away. So what practitioners have been doing forever is they just trim. They just take, oh, these are outliers, and let's just take the empirical average of the rest of these points. Okay, so this is called the trimmed mean. When we trim some epsilon fraction of the data, we forget it on both sides and take the average value. Okay? Now, even though this is a really old idea, you see people have studied it, its theory already in the 60s. It's only very recently when we realized, well, this was proved by Oliveira and Orenstein, that that the trim mean actually has sub-Gaussian performance if the amount of trimming is appropriate. And then what they proved is that if we chop off about log1/delta points from both sides of both ends, both extremes of the data set, then and take the empirical average of the rest, then we do have a sub-Gaussian bound. Okay, so I will show you how this works for an estimator which is a little bit a small variation, just because the proof becomes simple. So what we do is that we divide the data in two halves. Okay, I will denote the first half into x1 by x1 xn, and the second half by y1 yn. So we just have two n data points. They are all independent and identically distributed. The second half of the data is used simply to calculate the trimming points where we're going to trim for the second half of the data. And this trimming is based on the empirical quantiles. Okay, so we just y star epsilon n, this is just the epsilon nth smallest data point, and y star 1 minus epsilon n is the 1 minus epsilon nth smallest data point. Okay, so the star means that we order the y ones, the yi's. Okay, so we just take these empirical quantiles. Okay, so epsilon n on the left, epsilon n on the right, and these are gonna be these values alpha and beta. And now we just take this function here, okay, that I denoted by phi alpha beta, which is the identity function, but now we make it constant for values less than alpha and values greater than beta, and we just, instead of averaging the xi's, we average this truncated value of the xi's. Okay, and now for this estimator we have this beautiful sub-Gaussian property. Again, exactly the same form as before, with probability 1 minus delta. The error is at most sigma over root n times square root of log 1 over epsilon. Again, don't pay too much attention to the constants. All right. Okay. Just very quickly, let me show you why this works. So, first of all, by standard bounds for the binomial tail, for the binomial distribution, one can prove that this trimming. Remember, we used the 1/2 of the data just to estimate the quantiles, okay, where we want to trim. This is correct, right? Remember, alpha was the epsilon quantile, empirical epsilon quantile, so it will be between the epsilon half and the two epsilon quantiles with high probability e to the minus n epsilon. And we do the same on the right. Okay. So now, if we may decompose the error, so this is our final estimator, and the difference between the estimator and the mean is bounded by, well, the difference between, this is the expectation of this truncation function, right? And this is just the by how much the empirical average differs from its expectation. Okay. Now, this second half, this can be handled very simply, because now these are bounded random variables. This is the expectation of a bounded random variable. So it's very easy to show that this is of the right order, sigma over n times square root of. Sorry, this should be within inside the square root here. Okay, so this is of the right order of magnitude. And the bias, which is the difference between the true mean and the expectation of this function, phi alpha beta. Well, this can again be, okay, I'm not going to go over the details. You can read the slides after the talk. It's really, we just use Cauchy-Schwarz and really simple things. The Chebyshev's inequality, it just comes out very nicely. Okay. All right. Now, the trimmed mean has a very nice property that it is robust under adversarial contamination. So what does this mean? It means that that we may have an adversary that sees the data before us, before the statistician, and this adversary even can know what we do, what our algorithm will be, what our mean estimator is, and this adversary can modify a certain fraction of the data points in a completely arbitrary way, in a really mean and devious way. Okay. So let's say eta fraction of the data. Okay? But now you can just repeat the same proof that I kind of semi showed you, and see that if the trimming threshold is now, if you use an epsilon fraction, and this trimming now is either what is the maximum of eta and this log 1 over delta over n. So this log 1 over delta over n, this was the fraction of the data that we trimmed before when the data was clean. Now, if this eta is bigger than that, then we will trim more points. If it's smaller than that, then we trim the same number of points. Then the trim mean estimator satisfies this inequality that the error is bounded by what we had before, plus an additional term, which is like sigma times square root of eta. Right? Remember, eta is the fraction of the data that the adversary is allowed to modify. And one can show that this is the best one can hope for. Okay? And this is really easy to see that the adversary can fool any estimator up to this level. Okay? But the trim mean automatically does the optimal if the trimming level is chosen. So this is the trim mean estimator is robust not only with respect to heavy tails, but also with respect to contamination in a very strong sense. Okay. Now, if the distribution is nice, let's say if the distribution is sub-Gaussian, then this square root of eta can even be improved to almost eta times some logarithmic term. Okay. And again, that is optimal. All right. So this ends the first half of the talk, which was somehow preparation for the real content, which is estimating the mean of multivariate distributions. Okay, so now we have, instead of real random variables, we have now a random vector. So X is a random vector taking values, let's say, in a d-dimensional space. Many of the results I will mention actually hold in Hilbert spaces, or even more generally in Banach spaces. But I will just present. Let's just assume that these are random vectors taking values in a d-dimensional space. The mean vector is denoted by mu, exactly the same way as before. And again, I will assume that the second moment exists. The second moment is now a matrix. It's the covariance matrix, which is the expected value of x minus mu times x minus mu transpose. Okay, so this is the covariance matrix, and I will assume that it exists, and I don't want to assume anything else. Okay, so this is, again, you can argue this is a mild assumption, and somehow it's, if we don't have this, then it's difficult to say. Then of course we cannot expect such nice bounds that we will get here. Okay, so the goal is the same as before. Let's upon observing independent identically distributed copies of this vector, we would like to estimate the mean such that it has a sub-Gaussian performance. But of course, now first we have to determine what does it mean that an estimator has a sub-Gaussian performance. Okay, so to understand that, we have to check what happens if the data are actually distributed according to a Gaussian distribution. okay, according to a multivariate normal distribution. So if X is multivariate normal, then of course, then one can prove again that you cannot beat the sample mean. So let's look at what the sample mean does in the Gaussian case. Okay. Now, one can show easily that this kind of high probability bound, right? With probability at least 1 minus delta, the Euclidean norm of the difference between the empirical mean and the true mean is bounded by square root of the trace of the covariance matrix divided by n plus square root of the largest eigenvalue of the covariance matrix. So lambda max is the largest eigenvalue of the covariance matrix times log 1 over delta over n. Okay. So this largest eigenvalue is just the variance in the direction where the variance is largest. Okay. So among all directions, if we project our Gaussian vector in a direction, then it is still a Gaussian, and this is the largest possible variance. Okay. So this part is clearly necessary, and this part is also necessary because it's the expected value. It's the expected value of this difference, right? So in fact, the expectation of the Euclidean norm of the difference, well, this can be bounded, and here we really don't lose anything. That's very easy to see. Square root of the expected value of the squared norm, but this actually equals the trace of the covariance matrix. Okay, so the expected distance equals, or sorry, is bounded by the square root of trace of the covariance matrix, and the second term here, this comes from the fluctuations of this random variable around its expected value, and this follows from the Gaussian concentration inequality. Okay, so the Gaussian concentration inequality says that if we have a function of Gaussian random variables that's a Lipschitz function, then it is concentrated. And I'm not going to state the exact form of it, but let me just mention that this second term comes from the fluctuations of, well, the norm is of course a Lipschitz function, so Lipschitz function of this Gaussian vector, and that's where this comes from. Okay, so this is a sub-Gaussian performance, and now the question is, can we construct an estimator that has a sub-Gaussian performance of this form for all distributions with the second moment whose covariance matrix exists? Okay. All right. So, of course, now we can try to find inspiration from the one-dimensional case, and one of the obvious ideas is to use the median of means estimator. Okay, so means, okay, that's clear. What we can do again is that we form blocks of the data, and for each block we compute the empirical mean. So we have this. If we have k blocks, then now we have these k points in the three-dimensional space. And now the median of means idea says that now we should take the median of these points. Okay, but in high dimensions, what does it mean? What's the median of random vectors? Well, there are many notions. So for one very simple notion is the coordinate-wise median, right? So we project on each coordinate, we compute the median, and we look at the vector that whose components are the coordinate-wise medians. Okay. Another one is what's called the geometric median. Okay, the geometric median is just the point y in Rd that minimizes the distance to all the data points. So it minimizes the sum of the distances of all the data points. Okay, so this is also a generalization of the one-dimensional median, because the one-dimensional median is exactly this. When, of course, instead of Euclidean norm here, we just have absolute values. But now you can dream up many other notions of the medians. For example, you can think about the smallest ball in Rd that contains at least half of the points and the center of that. Okay, like I call this the smallest ball median. or there's the famous Tukey median, which I'm not going to define there, and many other notions. Okay? So now we can try to generalize the median of mean estimator by replacing the notion of median in high dimensions by one of these notions. Okay? So the coordinate-wise median is, now the analysis is completely straightforward. What we get is the square root of the trace of the covariance matrix divided by n times log d over delta. Okay? Now, first of all, I didn't emphasize this, but if you look at this what we call sub-gaussian performance, the performance of the empirical mean for Gaussians, this is an infinite dimensional statement. The dimension here doesn't appear anywhere. So the only thing that matters is the trace and the largest eigenvalue of this covariance matrix or covariance operator in the infinite dimensional space. Okay, so the fact that that we have d here is not so good. Okay, even though it's only in the logarithmic factor. The other problem is that here the trace is multiplied with the logarithmic term, and we would like the logarithmic term to be multiplied only with the largest eigenvalue. Remember, the trace is the sum of the eigenvalues. So in high dimensions, this can be much bigger than the largest eigenvalue. So if the trace is multiplied by log 1 over delta, then we lose. Okay, so this coordinate-wise median is not optimal for various reasons. Now let's look at the smallest ball median. This is very easy to analyze, and I'm going to show you in the next slide how we can do it. But one can prove. So now what we do again is we form blocks, independent blocks. We take the empirical average within each block, and now we take the smallest ball median of these points. Okay? And now what one can prove is that with probability at least 1 minus delta, the error, the distance between this estimator and the mean is bounded by a constant times square root of the trace of the covariance matrix times log 1 over delta divided by n. So the good news is that this is again dimension free, as it should be. On the other hand, this is not really sub-Gaussian because again the log 1 over delta is multiplied by the trace and not by the largest eigenvalue. Okay, so here's the proof of why this the smallest ball median has this nice property. So you see, since by Chebyshev's inequality, we see that that with probability at least 75%. Each of these blocks, each of these means within the blocks is within distance square root of trace divided by m. M is the number of points within one block. Okay, so this is exactly the same as in the one-dimensional case. Okay, so here's a little picture. So this is the true mean. Then we know that. So this is r. R is this quantity, the square root of the trace divided by m. Okay. So we know that each of these points falls within this ball with probability 75%. So that means that with huge probability, at least half of the points fall in here. Okay? Now, if this is our estimator, mu hat, this is the center of the smallest ball that contains at least half of the points. Okay? So in particular, the radius of this ball is also less than r, right? Because this is another ball, the true mean. The ball of radius r centered at the true mean has the property that it contains more than half of the points. So this is the radius of this ball is also less than r. But since both of these balls contain more than half of the points, there is at least one point that's contained in both of them. And this point is within distance r of mu, and it's also within distance r of mu hat. So the distance of mu and mu hat is at most 2r. Okay, so that's how we prove this inequality. Okay, so the smallest ball median, the smallest ball median of means estimator has this nice property it has a problem that computing this is actually a computationally hard problem in high dimensions. Okay, so you can prove that that there's no algorithm unless p equals np that can compute this in time which is not exponential in the dimension. Okay. Now, one can also look at the so-called geometric mean. Okay. And this was analyzed by Xu, Sabato, and Minsker, and in particular, Minsker proved that the median of the geometric median of means method also has this kind of property. Again, the proof is not too difficult, and the nice thing about this is that this is a solution of a convex optimization problem. This is a convex function of y, and in fact, really fast algorithms exist. So this can be computed really quickly. Of course, nothing is as computationally easy as the empirical average, but this can be computed very quickly, and it has this nice performance bond. But still, this is not sub-gaussian. So so here's a version that we came up with, that an estimator, a median of means type of estimator that we call median of means tournament, that does have a purely sub-Gaussian performance. Okay, so what's the idea here? The idea is that the mean, what is the mean vector? Well, a very simple property, a very basic property of the mean vector, in fact, you can actually define the mean this way, is that it is the minimizer of this quadratic function. Okay? So it's the little x that minimizes the expected squared Euclidean distance to x. Okay, that's the property of the mean vector. This is very, very easy to see. Now, then a way of trying to estimate mu is try to find the minimum of this function. Of course, we don't know this expectation, right? But we have data. So here's what we do. For any pair of points, we can try to guess whether A is better or B is better. Okay, and then we can set up a kind of tournament between these between all pairs of points in RD. Now, remember, for me, an estimator is just a measurable function of the data. So don't ask for now how this is computed. I will come back to it later. Okay. So again, what we start with this with blocking the data. We take k blocks, each of size m, and within each block we compute the empirical average. Okay. Now we say that a candidate point A defeats B, A is better than B, if more than half of the points, more than half of these centers are closer to A than to B. Okay, right? So this is just the orthogonal bisector. So more points should be on this part of in this half space than in this half space. Okay, this is when A defeats B. So then one can prove the following. If the number of blocks is as before, is about log 1 over delta, then with probability 1 minus delta, the true mean will defeat every point which is more than this distance away from the mean. Okay, so the true mean has the property that for any point that's far away, and what is far? Well, far is defined by this radius. The true mean will defeat every point that's outside of this ball. Okay, and this R is exactly the sum or maximum of these two quantities that we are after, right? The square root of the trace of the covariance matrix divided by n, and the square root of the largest eigenvalue of covariance matrix log 2 over delta divided by n. Okay. So now suppose that we know this, then it's very easy to come up with an estimator, which is this. So for each point in RD, we can look at the set of those points where set of those points where X defeats A. Okay. Right. So now this is a bounded set, right? Because if for each point, so if A is here, if I go far away, then the point, all the data points will be somehow in this half of the space. So A will be closer to more than half of the points than that one. So this is a bounded set for each point. Now we can look at the point in the space that minimizes the radius. Okay, so the radius of this set is just the farthest point in the set from A, from this center A. Okay. Now let's say these are strange sets. These are not convex. These are weird sets, but they are bounded. Okay. Now the lemma shows that the radius of the set, this red set S sub mu, right? The radius of the set of those points that defeat mu is smaller than R. Okay. But now, if this is our estimator, then this blue set is the set of those points that defeat mu and hat. Now, of course, this has even smaller radius because that's how we define mu and hat. Okay. But we know that well, either mu is in the blue set or mu and hat is in the red set, right? Because either mu defeats mu and hat or mu and hat defeats mu n. Only one of the two things are possible. So in both cases, the distance of these 2 points is less than R. Okay. So if you believe this lemma, then choosing the set that minimizes the radius of these sets, this is going to be the center of that, has a purely sub-Gaussian property. Okay, it has the property that with probability at least 1 minus delta, the distance, right? This distance is smaller than R, and this R is exactly of the form. Well, again, don't pay too much attention to the constants. They haven't been optimized, but they are just universal constants. All right. Now, okay, I wanted to say a few words about the proof of this lemma, but I'm not going to do this. So because I'm running out of time. But let me just say that the sub-Gaussian performance. So this is the main sub-Gaussian performance. So what this says is that if we choose the block size appropriately as log 1 over delta, then with probability at least 1 minus delta, the error of this median of means tournament estimator is bounded by this quantity, which is exactly of the sub-Gaussian form. And you see, this is this only assumes the existence of the covariance matrix. Okay, nothing else. All right. So I'm going to skip these few slides. So now, of course, this is not algorithmic, right? This is an existence proof. It's just what we prove is that there exists a measurable function of the data that has this, that's an estimator that has this nice sub-Gaussian properties. Now, after our work, people had started to work on actually computable, efficiently computable versions of it. And Sam Hopkins at Berkeley came up with a semi-definite relaxation of this estimator that can be computed in polynomial time, in time n times d plus a polynomial of d, and k was the number of blocks. Okay? But this 8th power is not the best. This has been, people have been working on this, and this has been improved. Now this exponent is down to 3, I think. Okay? So efficient ways. By efficient, I mean it's time polynomial in D, so it doesn't grow exponentially in D, exist now. Now, yeah. So there's another way of constructing sub-Gaussian estimators, and this can be based on the other idea that I mentioned in the first half of the talk, the trimmed mean estimator. Okay, so this is a multivariate trim mean estimator that we analyzed, and so here's what we can do. we may divide again the data into two halves, just like before. And now for each direction, right, each vector in the sphere, so in each direction, we may project the data in that direction and compute compute the empirical epsilon half and 1 minus epsilon quantize based on the second half of the data. And now in each direction, we can take this trimmed mean estimator, right? So these are the projected data points projected to the direction of v, and this phi is the same trimming function that I mentioned earlier. Okay, so alpha v and beta v are in this projection, they are the epsilon and 1 minus epsilon empirical quantize computed from the second half of the data. Okay, so we compute this, but you see here I have to widen the range a little bit by narrow the range a little bit by taking this q and subtracting some number q and adding some number q. This q is a parameter here that I will explain where it comes from. Okay. And now we can once we just project in one dimension, do the trimmed mean estimator, and for this trimmed mean now we take this entire slab. Okay, right? So now we take all the x's whose projected value is close to this value. Okay, and now we just take all possible directions and take a point, take the set of the points that fall in these slabs. Okay, so these slabs are kind of confidence intervals in all possible directions. They're in all possible directions on the sphere. Okay, and so now this depends on this parameter q, and now we take the smallest q such that this set is still not empty. Okay, and now we take a point in that. So this is our estimator. Right? This is the multivariate trim mean estimator. So in each direction, we take a trim mean estimator, and we look at the vector that falls in all these sets. Okay? And we can prove that if this q is so what we can prove. Okay, let me just go to the theorem. Sorry, no, this is the theorem. Is that this estimator automatically finds the right value of q by this trickery here, and it has this purely sub-Gaussian performance. Okay, so this multivariate trim mean also gives it's a different principle that also gives the sub-Gaussian estimator. Okay, and the advantage of this multivariate trim mean compared to the median of means tournament is that this is robust against adversarial contamination. So just the same way as in the univariate case, if there's an adversary that can arbitrarily manipulate an eta fraction of the data, then the exact same trim mean multivariate trim mean estimator that I just described with this trimming this trimming value. Okay, so now if eta is larger than this value, then we have to trim more points. It has this bound, this performance bound. It has with probability 1 minus epsilon, 1 minus delta, the Euclidean norm of the estimator, the difference of the estimator and the true mean is bounded by what we had before, right? This is the purely sub-Gaussian term, and plus a term. This is the price of price we pay for adversarial contamination, which is proportional to the square root of the largest eigenvalue. Sorry, this lambda one is actually lambda max. These are the same things. So the largest eigenvalue of the covariance matrix times eta. And again, this is necessary. Okay. So any estimator has to have this term. If the distribution is nicer, if we know that it's sub-Gaussian, then this term can be improved. So again, this square root of eta becomes essentially eta. Okay, now this is, of course, there's again, this is just an existence proof, which because computing in all there are uncountably many slabs. You can make this algorithmic by taking a discretization of the sphere, but it will have exponentially many points. So we can convert this into an exponential time algorithm, but that's of course not practical. Now, very recently, this paper came out where they actually propose an efficiently computable estimator that has the same kind of bound even under adversarial contamination. And I think I will end here. We'll skip a few things here. And these are the references. So you can see there's a series of paper that I wrote with Shahar. And there's a very recent one that I didn't have time to talk about, but maybe next time.
Well, thanks, Gábor, for this nice talk. Are there any questions or remarks? Any questions?
Yes, I have one.
Yo tengo una pregunta, Karma.
Sí, digas. I think first Argimiro.
Vale, gracias. Gracias, Gábor, por esta fantástica charla. Tenía una pregunta técnica de curiosidad, ¿no? La técnica esta del testing para probar la robustez del estimador usando el adversarial contamination. No me quedó claro si esto lo haces una sola vez o se aplica N veces y cómo estimas estas N veces que debes de aplicar el adversarial contamination. Y entonces, ¿qué tomas luego? ¿La media de los valores que consigues o?
No. Okay. So here the adversary can do whatever it wants with the data. And you just use this estimator and then it has this guarantee.
All right. You just you apply the adversarial once and then you prove that you get an estimator which is close to an estimation which is close to the one you had without the adversarial.
So the adversary is allowed to do anything it wants with 5% of the data or 2% of the data in any way it likes, and then these estimators are still doing well.
Okay, I thought it was similar to the techniques of bootstrapping where you apply several times just to see. No. Okay. Nice talk. Well, anyway, maybe I hope these slides will be available. If not, I'll ask them from you. Okay.
Thanks.
Vale, Joaquim. Joaquim? Sí. Tú ya puedes hablar, sí, digas.
Hello, Gábor, Joaquim Bruna.
Hola.
I have two questions related to this median block estimator. So in the Scholar case, if I understood correctly, I mean the way you define the blocks is just looking simply by the order of the sample.
They have to be independent.
My question.
Yeah.
No, but the way you define the blocks is you take the sample in an ordered way, no?
No. By index, ordered by index. It's not ordered. No. They cannot be sorted. That's very important. They have to be independent. So you shuffle the data first, and then you take the blocks. That's very important. I should have emphasized that. Yeah,
okay. And then another thing regarding the same situation, but in the vector case. Either my question is stupid or not. I mean, I don't know, but that's the question. I mean, my question is how this depends on the system of coordinates you choose to represent the sample. I mean, either is invariant by change of coordinates.
Yes, it is.
Or else, is it better to exhibit the sample in a suitable coordinate system in which the estimate will improve?
Yeah. So the estimators that are purely sub-Gaussian that I showed, they are independent of the coordinates. They are rotation invariant.
Yeah, so, but I mean, does it make sense that, for example, to choose the best coordinates in which it might makes a sense that the estimate might improve by choosing a special system.
So if you use an estimator that depends on the coordinates, for example, if you use the coordinate-wise median, then of course it makes sense, right? Because but the estimators that I propose, they are independent of the coordinates, right? They're all rotation invariant, so it doesn't matter. But if you have an estimator, of course, that's actually a good question. So if we look at this estimator, the coordinate-wise median, then maybe you can do something better by choosing cleverly a transformation. But yeah,
then I have a third question that, again, I mean, is not it's just an intuition. No? Is that you do in the vector case you use the Euclidean norm. And no, just by you know that in compressed sensing for many things, it turns out that the L1 norm is best suited.
Absolutely.
So my question is whether in this setting that you are working, this is also a possibility to consider or not.
So you see, we have a whole paper on this. And here, with respect to general norms, yeah, I didn't mention this, but yes, we extended this to when you give me a norm and you say you want your estimator to be optimal in that norm. So
no, but is the L1 norm best suited for or not?
It depends. So many times, if you want to, for example, matrix norms are used, right? When your data come in matrix form, then it's some matrix norm, and it depends on the application what norm you want to prefer. Yes.
And
yeah.
Okay. No, one final question: Are those estimators being used, you know, in I don't know, in machine learning or in
So in my class, I usually ask the students to simulate and to see. You see, they are. So if you the trim mean definitely. I mean, if you're afraid of heavy tails or contamination, then you have to do something. And the trim mean has been used forever in statistics. This median of mean estimator, I don't really know if they are used in practice. So when you simulate them in one-dimensional data, they actually work nicely. So and for heavy tail data, they do beat the empirical mean. But how practical they are, you see, one of the problem is that there is a parameter which depends on the confidence level. Okay. So it's you have to be inventive somehow.
So, well, just to say that, you know, Gábor is the second seminar I attended from you in the last month.
Oh, really?
Okay. And I must say that I enjoy both very, very, very much.
Okay.
And I congratulate you for all these results.
Thank you.
So, are there any more questions?
Yes, Carmen?
Yes, sí, dime, Santiago.
I have something very short curiosity. So, Gábor, have you considered mean estimators that use differential privacy techniques?
That's a very good question. Not yet, no. But there are some papers now in the computer science literature where people do look at this kind of questions. Yes, right. Of course, that's really important. Yeah, absolutely.
Okay. Thank you, Gábor.
More questions? Well, if not, let's thank the speaker again. Thank you, Gábor. And in fact, we have like 5 minutes to start the next talk. José Antonio, pardon.
Okay, so we take 5-minute rest.
Yeah, we can have 5-minute rest, or maybe you can put your slides here and try it.
Does it works?
Mm-hmm.
Ok.
Lo puedes poner en presentación, quizás, ¿no?
Sí, sí, está en presentación ahora.
Mm,
¿No la veis en presentación?
bueno, lo vemos con todas las herramientas de Adobe, ¿no?
No deberíais, yo lo estoy viendo en presentación, pero vale, voy a hacer otra cosa. La voy a poner en presentación y la voy a compartir cuando esté en presentación. Vale, a ver si así funciona. En principio está mostrando la pantalla y la pantalla yo la pongo en presentación. A ver ahora si funciona. ¿Sigue igual?
De momento está ahora lo veo negro yo.
Oh my God. Hasta el acróbata cascado. No.
Vaya. Bien que tengamos 5 minutos.
Sí, sí, sí. A ver, vamos a probar de nuevo. Vamos a ver. Vale, voy a ponerlo en grande y luego lo comparto. ¿Vale? Ya está en grande y ahora voy a intentar compartirlo desde Zoom. Entonces, share screen. ¿Qué me decís ahora?
Ahora sí.
Vale.
Ahora sí se ve bien. Perfecto.
Ese era el truco, entonces. Vale, muy bien. Pues nada, damos 5 minutos entonces.
Sí. Si quieren tomar un café.
Para que descanse, sí.
¿Eh?
Muy interesante, Gábor. Súper interesante.
Carme?
Gracias, gracias.
Digues, Joaquim?
No. Esteu aquí. Que fem un descans, així o no? Sí, no?
De 5 minuts, que començava a ir 20 i estàvem provant per si algú vol anar a prendre un cafè o així.
Gabor.
Dime, dime.
Oye, bueno, yo no sé cuánta gente. Oye, ¿cómo va la bici?
Bueno, va.
44 te oyen.
No sabía yo, Gábor, que tú eras aficionado a la bici también.
¿Qué tal estás? ¿Qué tal va tú?
¿Vas al pueblo, a Gresha o no?
Hace mucho que no he ido, pero sí, de vez en cuando sí.
A ver.
Bueno, ahora es complicado.
Todo es complicado ahora.
¿Estáis en Cataluña?
¿Cómo estamos?
Pues
está bajando un poco el factor este del RT, pero aún hay mucha gente en la UCI, y bastantes muertes cada día, 100 y pico hoy me parece. ¿Y vosotros?
¿Restricciones?
Y 3.700, hoy 3.700 contagiados, aún muchos. ¿Y vosotros cómo estáis?
No, nosotros estamos jodidos también. Eso, el RT está cercano a 1, pero estamos ya ahora, yo creo que en la cresta de la ola. Estamos teniendo unos 1.400, 1.500 por ahí.
¿Y tenéis toque de queda también y confinamiento perimetral?
Sí, tenemos toque de queda a las 10 y no podemos salir solo podemos ir al municipio colindante a hacer actividades sociales o deportivas.
Lo mismo que nosotros. El fin de semana, solo el fin de semana, ¿no?
No, durante toda
la semana.
Sí.
Nosotros solamente el fin de semana.
Sí. Y luego los bares están cerrados, o sea, toda la hostelería está cerrada.
Aquí también.
O sea, no te puedes ni tomar un café.
No, aquí tampoco.
La máquina.
Y las clases en la universidad todas no presenciales.
Sí, no, nosotros aquí mantenemos todo, eso sí que lo estamos manteniendo.
¿Sí?
Sí, lo están manteniendo eso. Las clases sí, afortunadamente, porque yo empezaba clase el lunes, entonces, bueno, dije, qué bien que tengo presencial. ¿No? Es un tostón.
Wow.
Sí, no es un tostón. Pero bueno, a ver, yo creo que con estas medidas espero que se baje. Esperemos que se baje lo suficiente.
Sí, el problema es que se mantenga y no vuelva la tercera ola que dicen que llegará en enero, ¿no? Si no sé.
Me parece a mí que conocer qué es lo que va a pasar. ¿Alguien adelantó que íbamos a tener una ola ahora? ¿Y cuándo iba a ser? Yo creo que si lo hubiesen adelantado, si alguien hubiese sabido que iba a haber esto, pues igual, ya sé que a los políticos les cuesta escuchar a los científicos, ¿no? Pero si alguien hubiese sido capaz de adelantarlo, igual hubiesen podido tomar medidas antes.
Pero sí se había dicho, ¿eh? Se había dicho.
Se había dicho que en octubre, noviembre, ¿no? Habría eso decían, ¿no? Al principio.
Sí. Pero bueno.
Sí.
Era muy importante dejar entrar todos los turistas por
Claro,
vacaciones.
pero quiero decir, tú lo dices y si aciertas, acertaste. Pero si no aciertas, no apareces. Entonces, claro, el que lo ha dicho y sale dice, uy, qué bien, ha acertado. Yo creo que es muy difícil saber. O sea, yo todavía me pregunto por qué ha pasado que de repente haya crecido el número de contagios así de repente a mitad de octubre. Que hubiese aparecido antes, cuando empezaron las clases en los colegios, a mitad de octubre o un poco más tarde casi.
Sí, y en todos
La
sitios.
gente se confía y entonces
Sí, ha habido relajación, pero los contagios han crecido casi como han dado un salto.
Pero ha sido, sí, y además está tan universal, porque en Europa del Este en la primera ola no existía, y ahora, de repente,
sí, en todas partes.
En todas partes a la misma vez.
Sí, y en Estados Unidos también tuvieron algo parecido, pero en verano. Tuvieron algo parecido en verano, no sé. No sé.
Bueno, ya es y 20. ¿Empezamos?
Cuando queráis.
Vale. Pues empezamos, venga. So our next speaker is José Antonio Lozano, who works in statistical machine learning and combinatorial optimization. And he will talk about an introduction to time mining series. So, Antonio, cuando quieras.
Okay, thank you very much, Carmen. First of all, I would like to thank Luis to organize this colloquium. I don't know if it was exactly Luis who organized, but I know that Luis was behind the organization of the colloquium. So I think it's a good thing to try to establish relation between BCAM and BGSMath. So it's a pleasure to be here. So my presentation, there is no formulas in my presentation. No, I'm very sorry, no formulas in my presentation. So it's a completely different presentation and it's more computer science oriented, let's say. Okay, so what I'm gonna talk about is how to deal with time series when you want to carry out data mining activities. Okay, so I will mainly talk about algorithms and how to use time series with data mining activities. Okay, so basically this is the outline of the presentation. I will start talking about time series and data mining activities on time series. We briefly talk about clustering, then supervised classification, something about outlier anomaly detection, and then some conclusions and future work. Of course, you can stop me when you want. Okay, so basically all these appear because now we have a lot of time series around. I mean, for instance, in the Basque Country, we have a tradition of industry, and now we have a lot of time series that come from industry 4.0, from machines, from welding machines, from different kind of machines. And of course, these people in the companies, they have realized that it's important to analyze this series. We have many information about wearable. I mean, we all have a watch that can record our pulse or can record how many steps we do, etc. Or we can think about a weather forecast that is a clear case of time series analysis. Even when sometimes there is no dependence on time, we can also consider some data that could be considered as time series, even when they are not really time series. No, this is the case of this the way in which this Alexandria is written. Okay, so we can create time series from this image, for instance. Okay, so because there are that many series, it's important to, I mean, the community around machine learning has started to develop methods to deal specifically with time series data. Okay, so here you can see a mathematical definition. At least I'm going to put a mathematical definition of what is a time series. So basically, a time series is an order of pairs where we have some time stamps where each time stamp we take some values that these values xi can be univariate or can be multivariate real values. The main characteristics of time series is that there are some temporal correlation. And this is the main difference with regular data in machine learning. In this case, we have temporal correlation. Of course, it's quite common to have high dimensionality and also to have noise. You can imagine that time series coming from machines, they have a lot of noise because of the sensors. They are not completely precise, or they sometimes stop working, etc. Okay, so the most common activity with time series that probably has a long history is time series forecasting. Okay, in time series forecasting, we like to predict the future values of the series. Okay, so we have the stock market prediction. We want to know what is the value, the stock value of Movistar in the next 2 days, for instance, or in the next hour. Or we want to compute, we like to forecast the temperature that we will have in Barcelona and in Bilbao in the next 2 hours. Okay, but we are not going to talk about forecasting. Okay, it's a different problem, and we are not going to talk about forecasting. We are going to talk about, we are going to see time series as instances of some data mining activity. In this sense, we are going to consider, or our goal is to, our object of a study is to work with time series databases. So my source data are time series databases. They are usually big, they can have different length, they can be multidimensional, they can be of different kind. Okay. And the activities, the most common activities to carry out with time series are the typical activities in data mining, as to carry out clustering. No, imagine I have the consumption of the individuals in Bilbao, the electricity consumption of the individuals in Bilbao, and I want to cluster those individuals that have similar energy behavior consumption. Okay, this is one of the typical activities we can do in data mining, but we have to do with time series. Okay, another typical activity of data mining is classification, supervised classification. We have a set of time series. Each time series has assigned a label, and I construct a classifier that when a new time series comes, I guess the label for that time series. You can imagine we have the electrocardiogram of some patients. Some of them, they have a disease. Some of them, they are healthy. And then I construct a classifier to identify those patients that have a heart problem. And when a new electrocardiogram that at the end is a time series comes, I decide if it's healthy or is not. Okay. Another typical activity in time series data mining is to find anomaly or outlier detection. This is mainly in the industry scenario where they have a machine and they want to know when exactly the machine starts to behave improperly, or particular points where the machine didn't behave as expected. Okay, and this is what we are going to develop with some detail. I'm not gonna enter in specific details. I'm just gonna give you whole ideas of the topic on which are the most typical techniques that has been used in this area. I'm not gonna talk much about deep learning, but of course there are deep learning, mainly in the last year, they appear many deep learning applications to time series classification or anomaly detection. Okay. Another common activity is segmentation, where the goal is to codify the series in a simpler way, in such a way that the amount of memory we need to codify the series is small, but we keep most of the information that is contained in the series. Okay, we are not gonna comment about segmentation, but we will talk about the other three topics. Okay, so let's start with clustering. So basically, what the problem consisted. I've been given a database of series, time series, and I want to cluster the series in such a way that the series that are similar are in the same group, and those series that are different are in different groups. The electricity examples I gave at the beginning is a typical example of this kind of why I would like to do time series clustering in reality. Okay, so the main difference with the classic clustering is that when we want to carry out clustering in time series, we need to take into account the correlation, the temporal correlation of the time series. Okay, when I have points in Rn, I don't mind, there is no temporal correlation, but particularly in time series, I have temporal correlation. And apparently, or it should be convenient to have this temporal correlation into account when we carry out clustering. Okay, so if we think in a typical clustering algorithms or clustering technique, one can think that we can carry out a kind of hierarchical clustering with the series, or we can do some partitional clustering using k-means. Okay, but if you try to do that with time series, at the end, what we need is a distance between series. Okay, all these clustering techniques are based on the use of a distance. So we need to define a distance between time series. Okay, before carrying out the clustering activity, we need to define a distance for the time series. In general, there are two types of distances for time series. One distances are rigid distances, where what I do is to compare one point of one series with the same point, with a point in the same time in the other series. Okay. In the case of flexible distances, these flexible distances allow to construct the time or to work the series to modify the time scale of the two series in order to compute the distance. Okay, the most typical example of rigid distance is the Euclidean distance. I mean, we can compute the Euclidean distance between two series, and this can be used as a distance between series. The good point is that it's easy to compute, but it can only be computed for series that they have the same, only for series with the same distance, no, with the same size. Okay, they can only be computed for series that they have the same size. Another important thing is that this distance do not take into account the correlation, do not take into account the time, okay, and is quite sensitive to noise. Okay. On the other hand, we can use the dynamic time warping. Okay, the dynamic time warping is the most common distance between time series, and what it does is to trying to find the shortest path in terms of distance between the beginning and the end of the series. So in such a way that the distance can compare one point of one series with several points of the other series. Okay, in this case, it compares this point with these 4 points of the other series, and so on. So it takes into account the order of the sequence. Okay, it takes into account the order of the sequence. It takes into account at some point the correlation of the time of the time of the series. Okay, it can deal with series of different size, but unfortunately, this dynamic time warping is quite expensive computationally because it's a square. Okay, the computation it's always square. Okay, so even it's a good distance for time series, it's a little bit expensive. We can think here is an example of, move myself. Oh, I can't. Okay, here are an example of a couple of clustering, one with Euclidean distance and one with the dynamic time warping. Okay, with the dynamic time warping, it tried to cluster put in the same cluster those series that they have more or less the same shape. or it's similar in shape. They have similar patterns, okay? In the case of the Euclidean distance, as the Euclidean distance does not take into account the time, it can join series that are quite different, okay? So most of the time, the most convenient distance is the dynamic time warping, okay? Okay, fortunately, there are some cheap version of the dynamic time warping that can be calculated in linear time by restricting the path in which we can join different points of the different series. So basically, I don't allow to join this point of one series with, for instance, this point of the other series. You have to join this point with points that are closer, okay? So it's not as free as the original dynamic time warping, but still takes into account the time, okay? And there are other distances, other elastic distance, for instance, the edit distance for real sequences, and there are several distances based on this edit distance. So basically, this distance take into account in order to define the distance between two, in this case, between two sequence of symbols, you take into account the operation of delete, substitute, insert, substitute, in order to reach one from the other. Okay. In this journal paper, you will find software when there are many different distances codified, so you can use freely. Okay. So there, for the elastic versions, there are some online versions that can be used for streaming also. This is, in this case, what the distance does is just to forget a little bit the past. Okay, to forget the past in order to compute the distance between two streaming time series. Okay, so there are some alternatives for calculating distances. Okay, one alternative that we will see later on for supervised classification is representing each series by means of features. Okay, and then calculate the distance between the features. For instance, we can think in we can use shift. We can use as a feature. You can use shift. You can use average. You can use different features and then compute the distance between features. Another common possibility in the literature is to use a parametric model. For each time series, I learn a parametric model and then I use the distance between the parameters of the parametric model. Okay, these are two alternatives to the use of distances. Okay. All in all, it's important to say that, of course, there is no best distance. There is no free lunch in this case. Okay, we cannot say this is the best distance. Okay, and each problem requires a different distance. Okay. Furthermore, I mean, the most important thing is the distance we use has to be in agreement with our knowledge about what is far and what is close, and it depends on the application. For instance, if we start to work with electrocardiogram, the physicians can give you an idea of what is close and what is far. Okay, and the distance that you define can be in agreement with this knowledge. Okay. So our hint is to try with several distances to see what is going on. Okay. One of the challenges is to design a method to the semi-automatic selection of a distance, and semi-automatic in the sense that it would be nice to include the person that is going to use the system. Okay, the person that is interested in the clustering, in such a way that this person can choose the most appropriate distance for the problem at hand. Okay, we did some work on the automatic selection of a distance. Okay, but however, we think that the inclusion of the user is really important in this case. Okay. Okay, if we come back to the clustering problem, and imagine I want to do I want to use k-means to carry out clustering. Okay, if I want to use k-means with any of the distances, for instance, with the dynamic time warping, we need to calculate the centroids. And this can be computationally expensive or even can be senseless. Okay, so in many occasions, what people do is to use camedoids in which the centroid is the representative is one of the points, one of the series in the data set. Okay, so some remarks on clustering is that there are some recent papers on the computation of a mean of a series. Okay, so there are people working on what is the mean of a series. Of course, we can use the Euclidean distance, but most of the time what you get, it makes no sense. And there are almost no publications related with alternative clustering methods like graph-based method of spectral clustering or model-based clustering in the field of time series. Okay, so there are many work that can be done in this area, and also the work on multivariate time series clustering is not really big. I mean, there are some papers, but there are not many papers on the topic. Okay, so now we're going to talk about supervised classification. Okay, so when we have to deal with a supervised classification problem based on time series, we have to make a choice, and the choice is, can I use general purpose classifiers, or should I use a specific time series classifier? At the end, we can consider a time series as a vector and then use off-the-shelf classifiers to carry out a classification. Okay, or design specific methods for time series. Okay, in the first case, if we use general purpose classifier, what we do is to consider that each series is an instance and each time stamp is considered as a feature. So it's like we have a data set like that, and this classifier, they do not take into account that, for instance, I have T2 before T1. They do not consider the order. Okay, so at some point, if we are using general purpose classifier, we are discarding the order information that it should be in the time series. Okay, so the idea is in general to use time series specific classifier, but however, in some scenarios, it seems that general purpose classifiers, they work as good as time series specific scenario. So a good point of research is to know when general purpose are enough to reach good results, and we don't know time series specific scenarios, specific classifiers. Okay, so the problem with time series classification is what is relevant? What is the relevant information in time series classification? I mean, we can think in this problem. Okay, this is problem 1, in which this series, they have label 1. This series, they have label 2. Okay, this is usually done to ask the people in the audience. So what is the relevant information here to distinguish between problem 1 and problem 2? Okay, because there is no audience today, so I will say. So clearly, the relevant information is the shape. Okay, the shape is the relevant information. Now here we have one shape, here we have other shape. So these belong to class 1, these belong to class 2. However, in the second problem, these are in class 1, these are in class 2. But they have almost the same shape. Okay, the difference is where is the location of the shape. Okay, the location of the shape is here in label 1. The location of the shape is at the beginning in label 2. Okay, so in the first case we rely on shape, on the second in location, and this is the real problem. I mean, what is the relevant information in a time series classification problem? For instance, in this case, it's clear that the temporal correlation is really relevant. At the same here, temporal correlation is really relevant, but it's not clear which the main properties of the series are in order to create really efficient classifiers. Okay, so I'm gonna give you some ideas on on how are the classifiers that have been proposed in the literature to deal with time series. Okay, and we can distinguish between classifiers based on distance, classifiers based on models, and classifiers based on features. Okay, in the case of distance, we carry out a taxonomy, and basically we can distinguish a K and N methods that they dominate the field, method based on distant features and distant kernels. Okay, I will go a little bit for each one of them just for you to have an idea. So the most common classifier in time series is the the one nearest neighbor. Okay, and it's the baseline method. If you want to design a new time series classifier, we always use the one nearest neighbor as the baseline. Okay, as the baseline benchmark. So it's very basic. We have the time series training data set. When a new series comes, I compute the distance to any of the time series in the training set, and the closest one is the label. The label of the closest one is the label that I assign to the new time series. Okay, in this case it's default that corresponds with this one, so I assign label 2. This classifier is easy to understand. It gets better results with higher number of series. However, it's computationally costly. And of course, we have the challenge of what is the most appropriate distance to use in this nearest neighbor. Of course, most of the application, they use the dynamic time warping, but sometimes for instance, when you have a big collection of time series, Euclidean distance works many times as good as the dynamic time series because you have many series. Okay, going a step forward. So what we can calculate is what is called distant features. What I do is for each series, I compute the distance to all the other series. So now I represent each series by a vector of distances. Okay, so each series is represented as a vector of distances. Once I have done that, what I have is that these are vectors. Okay, given that they are vectors, I can use any classifier of the self-classifiers, regularly constructed for vectors. Okay, so doing this transformation, I can use regular classifier. I do not take into account the temporal information. At some point, it's supposed that the temporal information it's in this matrix. Okay, when a new instant comes, I compute the distance to the rest of the series, and using this classifier, I compute the label. Okay, so as you can see, one of the tricks is to try to find a representation of vectors of the time series. Okay, in this case, the good point is that any general proposed algorithm could be applied. The bad point is that it depends on the number of series in the training set. If we have a very big training set, then I have to compute many distances, okay, and my vectors are really long. And then I also have a problem that is computationally expensive. Okay. So another alternative, this is what we call distant feature global, because I take into account all the distance, all the series to carry out this computation of distances. There is an alternative that is to compute these small pieces of the series that are called shaplets. Okay, these small pieces of the series are called shaplets, and what I do is to do almost the same as before, but now what I do is to compute the distance between each series to these shaplets. Okay, so I construct a distance matrix, but now I instead of computing the distance between each series to all the series, I compute the distance between this and these local patterns, okay? These local patterns that are good for classification, okay? Lij can be distance or can be present or absence. So it can be 0, 1, or can be a real number, okay? Again, it's computationally expensive because the computation of these shaplets is by means of an optimization process that is relatively expensive, okay? The good point is that when the shaplets are relevant, they obtain extremely good results. And what is better in these times of trustworthy artificial intelligence, and they are easy to interpret, okay? If they are easy to interpret, these shaplets are easy to interpret. So you can say, okay, this series is classified as 1 because it contains this shapelet and this shapelet, okay? So this is another way to use distant features, but using also only local information. Okay, another one in the literature, but this is really difficult to use, is to try to find a set of vectors in such a way that the distances between each vectors are exactly the same as the distances between the time series. Okay, while the idea is interesting because many classifiers are used in vectors, no, in Euclidean vectors, it's difficult to carry out. I mean, it's high complex, and also the prediction is not clearly what could be done. Okay. So another possibility to use distances for classifying time series is to construct a kernel matrix. Okay. In the case of PSD kernels, all the super vector machinery can be used to generate the cluster, but sometimes they use indefinite matrices. Okay, so the theoretical properties are lost, and it is easy to define, but however, you lose the properties of the super vector machines. Okay, a typical kernel is what is called the Gaussian distance substitution kernel. Okay, in which you substitute this Gaussian kernel. In this Gaussian kernel, you use for instance, the dynamic time warping or other kind of series. Okay, so this was the previous approaches were the distance-based approaches, and now we have the feature-based time series classification. In this feature-based time series classification, what we do is to compute some features of the series for each of the series. Okay, these features can be of different kind. Okay, and then again I have vectors. Okay, because I have vectors, I can use any classifier, any regular classifier to classify new instances. Okay, when a new series comes, I compute the features and I use the classifier to output a label. Okay, so the good point, some kind of features can be mean, variance, autoregressive coefficient, Fourier coefficients, SIF, trend, etc. Okay, in this paper, in time series features, you can find more than 100 features that could be used to extract features from the series. Okay, so the good point is that the representation is independent on the number of series. This is different of the previous methods that the representation in some of the methods depends on the number of series. The representation can be interpreted because these features can have an interpretation, a clear interpretation. The shift, for instance, can be interpreted. The autoregressive coefficient can be also interpreted. So the question is, again, the same challenge: what features to use? I mean, what features are relevant for classification in one particular problem of supervised classification of time series? Okay. Finally, another possibility is model-based time series classification, in which what I do is I create a model for all the time series of a label. Okay, it can be a ARIMA model, for instance, and I create a different model for each of all the labels. And then when a new series comes, what I do is to assign the label of the model which gives the highest likelihood to the new time series. Okay, so this is another approach that has been used in the literature to deal with time series classification. Okay, now, I mean, in this case, I mean, if we choose the right model, if we have the appropriate model, the results are going to be good. Okay, however, it's difficult to choose the right model. I mean, it's not clear what is the model that will allow to classify the series properly, and sometimes, I mean, there is no model, okay, or at least there is no known model. Okay. Okay. So now we are going to change a little bit, and we are going to talk about, again, we are in a supervised classification problem, but this is a supervised classification problem specific for time series. Okay, it's what we call early time series classification. Okay, in this case, we want to classify the series before it finishes. Okay, we don't want to wait to have all the length of the series. We want to classify the series as soon as possible. For instance, here you have some example, early detection of failures in machines. I mean, I would like to detect that the machine is going to fail, but before I have all the series. Okay, so I would like to detect as soon as possible that the machine is going to fail, no? Or early activity recognition. I would like to detect that this person is running before it has finished to run. Okay, I would like to detect as soon as possible what is going on and before the series has finished. Okay, and this is a problem that is specific for time series. It's a specific problem for time series classification. Okay, so in this case, what we have to do is to try to find a balance between accuracy and earliness. So I would like to classify as early as possible, but at the same time, I would like to have a high accuracy. Of course, these two objectives are not in agreement, so they are opposite. So the early usually, the early I do the classification, the earlier I do the classification, the lower the accuracy, and the opposite. Okay. So in this case, the schema is as follows. I mean, I have part of the series, and I decide if I classify the series at this time or I wait for more points in order to classify the series. So I have to take two decisions. One decision is to classify or to wait for more data. Okay, I wait for more data and carry out a classification. No, that's the idea. So this has been done in the literature in different ways, but particularly we did a work on that, and the idea was to create a classifier for some instant timestamps. Okay, for some instant timestamp, we create a classifier, and then when at time t1 we classify the series, but if the classification had not enough confidence, we wait for having more data, and we wait for having more data until we could provide a classification with enough confidence. Okay, so that's the idea. The idea is you try to classify, produce a classification, but if this classification, imagine, is with more or less, imagine is with probability 0.45, 0.55, if in a binary problem, would you say, okay, no, I'm gonna wait for more points until you have confidence enough classification. Okay. As you can see, I have here multivariate time series classification and challenge. The classification of multivariate time series of early multivariate time series classification has been explored, but not so much. So there are many challenges that need to be taken in the field of multivariate time series classification. I mean, there are now more algorithms, but still it's a place where there are many things to be done. Okay. So just I'm going to give you some points about outlier and anomaly detection. Okay. That is another of the common activities with time series. Okay. So one interesting point is that in time series, outliers can have different meanings, probably also in regular data, but in time series particularly. Usually when we talk about outliers, we are thinking in unwanted data. So it's unwanted data. What we want to do is to do a data cleaning to improve the data quality for further analysis. But in time series, most of the times when we talk about outliers, we talk about an event of interest. So we want to detect that outlier, because that outlier means that the machine is not working properly, or that the patient has her problem, or so we want the interesting point is not, we don't want to delete these outliers. We want to detect them. Okay, we want to detect the abnormality. That's the goal. Okay, and then there are different type of outliers in time series. Okay, in time series we can distinguish the different type of outliers. One type of outliers is what we call point outliers, where we have some point that they are clearly deviate from the series. Okay, we can have also point outliers in time series, in multivariate time series. Okay, here is only associated with one of the series, but here we have a point with is an outlier for all the series in a multivariate time series. Okay, of course, it's important to take into account that the outlier depends on how we look at the series. I mean, if we look, I mean, it can be local to part of the series, or it can be sometimes global. Okay, so it depends on the scale. If I go really far and look the series, probably I don't see O2. I couldn't only see O1. So it depends on the scale in which we want to work. In addition to point outliers, in time series, we can also think about subsequence outliers. So we want to discover some subsequences that they behave in a different way as the rest of the series. Okay. In this case, this subsequence is clearly an outlier because it behaves completely different to the rest of the series. Similarly to univariate time series, we can also talk about two subsequence outliers in multivariate time series. Okay, in this case, we have a subsequence outliers for the whole series. And here we have a subsequence outliers only for two of the three series, and here for only one. Okay, and finally, we can also think in another type of outlier, that is series outliers, because we are in our instances are time series. We can have a time series. The whole time series is an outlier. Okay, we have 4 series here, and clearly the red series is really far from the other series. Okay, so this is a time series outlier. Okay, and in most of the occasions, I'm not going to enter in detail. In most of the occasions, in most of the detection methods, what they try to do is to see when one point is out from what is expected for this point. Okay, at some point we need to compute or to calculate what is expected from this point. And when I am far from what is expected for me, I say that this is an outlier. Of course, we can define many different methods to define normality, many different models to define normality, all kind of models, and the model depends on if I'm looking for point outliers or if I'm looking for subsequence outliers, etc. Okay. Here, I mean, the estimation of xt can be by mean of median, minimum absolute deviation, by mean of a model. I mean, there are different ways in which I can calculate an estimation of the point xt. Okay, in case of points, but in case of subsequences, you can do something like that. Okay, here is an overview. Is an overview of classification of outlier detections. So we can calculate the outliers in detection in time series in taking into account different x's. One of them is the input data that can be univariate or multivariate. The outlier type that can be point, subsequence, or time series. Okay, can be univariate or multivariate. The detection method can be univariate or multivariate. There are some detection methods that can only apply to multivariate methods, and also the processing mode. Some algorithms can work only offline, and some of them can work also online. Okay, and yes, some conclusion on future work. So there are some problems that has not been explored in the time series mining field, and some of them are some that I put here. I mean, for instance, time series subset selection is almost unexplored. Okay, so if I have a time series classification problem, do I need all the time series? Okay, if I have a multivariate time series classification problem, do I need all the variables, or I can select some time series? Okay. Also, there is not much literature about learning in weakly environment. We can think in semi-supervised time series classification, multi-label time series classification, crowd learning time series classification, and then there are no much activity on theoretical bounds on learning, on assumptions on the generating model. Okay, there is no much assumption on the generating model of the time series, and in this case, the help of Gábor and more theoretical people, it is helpful. But just the problem of how to which assumptions can I do about the generative model on the time series classification problem, it's by itself a difficult problem. Okay, so I have some conclusions at some point. No conclusions. It's all of future work. I think I missed some. Okay, and here are some collaborators that have worked with me in these topics. Okay, I'm supposed to have some conclusions. Okay, and that's all. Quick, I think.
Yeah. Well, thank you very much, José Antonio, so for such a nice talk, interesting talk. Are there any questions or comments? Any questions?
Yes, I have a question.
Luis?
Thank you. First to say that I am a fan of time series, and I like to study them by using filters, in particular using Fourier filters. I think that this is also an unexplored field. It can be improved. But my question is about what you have said about those matrix kernels to study the structure of the time series. I must confess that I never thought about in the way you are thinking about the structure of time series. If I understand well, those matrix kernels, in some sense, they are similar to what is the fast wavelet transform when converting data to wavelets, to express data in terms of wavelets. Here, the aim would be to express the time series in terms of a certain base of shapes that depend on the kernel. Is that correct, this philosophical approach?
Well, I don't know. The truth is that I'm not sure. I mean, there are some. Okay, let's start with the Fourier transform. There are some methods in supervised classification. What they have tried is to carry out the Fourier transform and using the coefficient to after that learn a classifier. Okay, using the Fourier coefficient to learn a classifier. So this has been at the beginning of time series classification, this was one of the approach that were used. In the case of kernels, I think the goal of the people is mainly to be able to use all the machinery of super vector machine, okay? All the machinery. So what they try to do is to create kernels that they have that at some point they are able to to recover the information, the temporal information of the time series. Okay, so as I told you here, the most common way to do that is to use this Gaussian transformation kernel. Okay, but there are other approaches. This Gaussian, I think, can you see the screen?
Not at this moment.
No. Okay. Yeah. Okay. Wait a minute. I'm gonna share the screen now for a minute. Can you see the okay.
Not yet.
Can you see the screen
now? Yes,
yeah.
yes.
Yes.
So this is the most common kernel using but these are general ways to create kernels. I think these are not specific for time series. The specificity comes with the distance you put here. Okay.
Okay.
This is general ways to create kernels, and the specificity comes with the distance. So you can use distance that are specific for time series to try to recover the information, the temporal information between the series. Okay. Maybe they try to go a little bit further, but I don't know the truth. To say the truth, I don't know.
Mm-hmm.
Okay. No.
¿Algo más, Luis?
No, thank you. Yes.
No. Yes. I think that there's another question by Edward Forer Ortiz. Edward? It is written in the chat.
Yeah, I understand. Yeah, I could see the could see the question. I mean, he said about what are the criteria to establish the appropriate confidence in early time series classification? How is the process to do this? Okay, of course it depends on you, because at the end it's a threshold. Okay, at the end it's a threshold. So in this case, we decide on a threshold, and we learn the classifier taking into account the threshold. So we learn the classifier taking into account that we consider a particular and specific threshold. Okay, so that you have to design in advance the threshold you want to use. Okay.
Yeah. Okay. More questions or comments?
Maybe I would like to make a comment, a general comment, maybe on both talks. First thing that I enjoyed very much both talks. I think that they were very interesting and very much on the point, and very much helpful from the multidisciplinary point of view. And maybe the second comment, which is more scientific, is that I think that those two talks today are a good example of the fact that we are saying already, we are making publicity, that the world of artificial intelligence and machine learning needs a lot of theory, a lot of good theory inside, and that there is rigor in this work, because there are colleagues of us that they think that this is kind of random territory. No, that there is rigor here, and a lot of rigorous theory can be put inside. And I think that today we have seen in direct in both talks this a consequence of this.
Anybody else? Well, then let's thank again the two speakers for those magnificent talks.
Carmen, there is one that want to make a
Can you hear me, Jose Antonio?
Yeah, I can.
Okay, so my question is very specific. I was wondering if you have, or there is in the literature, any recipe to distinguish when you should use clustering on the raw time series versus clustering on a parametric approach to the models of the time series?
Yes, I have no clue. I mean, for instance, we have tried not with clustering, but with supervised classification. We have tried to have a kind of we have tried to find methods to say for this data set you can use just regular supervised classifier. For this data set you need a specific time series classifier. And we got some results, of course, heuristic results, nothing mathematically stable, but it's really difficult because hidden in the time, there are many properties that is very difficult to even to see. I mean, even when you see time series, you can distinguish them, but there are some properties inside the series that is difficult to know what is going on. I told you we had a couple of papers on that, but we were quite not disappointed by I mean, we decided not to go that way because we didn't reach a good point. Okay, I can imagine that in clustering is probably the same.
Yeah, my experience is that, and my experience was that the noise level of the series among the possible groups is a key factor into whether to go one or the other route.
Yeah, in this case, it's very important to have the one that is going to analyze the time series dataset, the cluster at the end. For instance, one of the things we are trying to do is to involve the user in the election of the distance in such a way that we have created a system that the system shows some time series to the user, and the user says these are closer, these are closer, these are farther, and in this process we try to find the right distance to carry out clustering, putting the user in the way to decide what is the right distance.
Okay, thank you.
More questions? Well, then thank you for being here and take care.
Okay, thank you very much for organizing this colloquium. And next time it's in our
in our place, in your place.
Yeah. Okay.
¿Virtual o presencialmente? Who knows?
Ojalá sea presencial.
Ojalá sea presencial, sí.
Ojalá sea presencial. En fin, pues nada, muchísimas gracias.
Vale, gracias a vosotros.
Muy diferentes, ¿no? Muy diferentes las charlas. Necesitamos la ayuda de Gábor para que nos dé ahí, ¿cómo se llama? Hay modelos generativos de series, que no es algo nada sencillo. Modelos generativos de programas de series, de clasificación de series.
Sí, sí, sí. Pero muy interesantes y muy complementarias las charlas. Yo reitero mis felicitaciones porque me parece...
Sí, está muy bien.
Muy...
Lo nuestro es más pedestre. Lo nuestro es más pedestre porque al final...
Seguramente mucho más útil.
Bueno, no es diferente. Quiero decir, es más pedestre porque al final nos vienen aquí los de... Quiero decir, aquí hay mucha industria. Entonces nos vienen las industrias y nos dicen, oye, tengo este problema. Y dices, vale, bueno, a ver qué puedo hacer, ¿no? Entonces tratas de eso. También tenemos cosas más teóricas, pero tenía la charla... Digo, jolín, con Gábor, digo, tendría que preparar algo más teórico, porque tenía esto, digo, no me da tiempo, vale, va. Pero bueno, en fin, muy bien. Pues nada, un placer. Y a ver si logramos vernos en persona.
Espero que sí.
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 Por supuesto. A ver si salimos de esta pronto. Si pillan la vacuna ya y nos ponen en marcha.
A todos.
Exacto.
Venga.
Venga,
Adeu.
agur.
Agur. Bueno, Eva,
Bueno.
fantàstica a l'escreen que tens a darrere, eh?
Que t'agrada.
Hombre.
Bueno, el que passa